Hi there, folks. Today we're looking at geometric sequences. And remember, a sequence is just a list of numbers that follows a specific pattern. And so I can get from one term to the next term by doing a certain thing. Arithmetic sequences are when we were adding the same thing each time. Geometric sequences are simply when we're multiplying by the same thing each time. Okay? So a geometric sequence is basically when the pattern is multiplication. So a sequence in which every consecutive term is found by multiplying the previous term by a common ratio. All right? And the reason we state it as common ratio is to remind ourselves really that what I'm multiplying by could be a fraction. In other words, the pattern could be dividing by the same thing each time, and it's still geometric because dividing by something like 3 is the same as multiplying by 1/3. Okay? Dividing by 4 each time, same as multiplying by 1/4. Okay? And so it could appear as if the pattern is division, but well, that's still multiplication in a sense. It's multiplying by a fraction. So if we're multiplying by the same thing each time, we have a geometric sequence. Okay? For example, if I look at these guys, first of all, I just want to identify the pattern. I want to find the next couple terms, all right? And whether it's geometric or not, I can still find the next couple terms. But then I can determine if it's geometric based on how did I get those next couple terms? What was the pattern that I followed? And so if I look at something like this guy, to get from 2 to 8 to 32, the pattern is multiplying by 4. 2 times 4 is an 8, times 4 is a 32. And if I kept that going, times 4 is a 128. Times 4 again is a 512. And of course, I could keep going, and I could use my calculator to help me out on that. But now the question is, the pattern I used was multiplying by 4 each time, so is this a geometric sequence? And the answer is yes. Okay, the pattern was multiplying by the same thing each time, so therefore this is a geometric sequence. That's what it means to be a geometric sequence. Okay. If I look at the next one, I go from 160 to 80 to 40 to 20. From a just a realistic type of perspective, we would look at this and say, hey, the pattern is divided by 2 each time, and I could keep going. 20 divided by 2 is a 10, divided by 2 is a 5, and of course I could keep going. Divided by 2 would be a 2.5. or a 5/2 if I did it as a fraction, okay? And so the pattern is dividing by 2 each time, but now I ask myself the question, could I state that? Could I state the pattern is multiplying by the same thing each time? The answer is yes, it's times a half, okay? 160 times 1/2 is an 80, times 1/2 is a 40, times 1/2 is a 20. The pattern is multiplying by 1/2 each time, so yes, this one is geometric. If I look at the next guy really kind of throws students off because of the use of fractions here. And as soon as we see fractions, we get a little bit intimidated. It's a little more difficult to identify, well, what would be the thing I'm multiplying by if there is a thing that I'm multiplying by. And so as I look at this one, this one's a little bit on the easier side. You might be able to see it right away. But think of it this way. This is like over 1. So you could always look at it and say, okay, well, what do I multiply the numerators by? Is there a pattern there? And then separately, is there a pattern for the denominators? That kind of thing, okay? That won't always work because sometimes fractions, things cancel out and they reduce, all right? So sometimes that's a little tough, but as I look at this thing, this one, it works. I could say, oh, the numerator's multiplied by 3, the denominator's being multiplied by 2, so really what I'm multiplying by is 3 over 2. And so if I kind of kept that pattern going and multiplied by 3 over 2, 81 times 3 is a 243. The 8 times 2 is a 16. And then I keep going. The 243 times 3 is a 729. And then the 16 times 2 is a 32. And so I'm just multiplying by 3 over 2 each time. And the pattern continues. And so once again, yes, this is geometric. And it's geometric because I'm multiplying by the same thing each time, okay? That's what a geometric sequence is. The other thing is if you're really having trouble identifying what do I multiply by to get the next thing, here's the little trick that you can use. You can always take one term and divide by the term before it. Like, for example, here, take this 8 and divide it by 2, well, and you get a 4. In other words, 2 times 4 will give me the 8, and now I could check that moving forward. Same thing here. 80 divided by 160 is 1/2. And guess what? That was the thing I was multiplying by. By doing division there, I'm working backwards to see what would I have to multiply the 160 by to get the 80, okay? And then I can check it moving forward. And I can do the same thing here. 9/2 divided by 3. Now that's a little bit more difficult. 9/2 divided by 3 It's like 3 over 1. Dividing by a fraction, same as multiplying by the reciprocal, okay? And as I start to reduce this thing, well, that gives me a 3 over 2, and that's the thing I was multiplying by each time, okay? And keep in mind that, that won't always give me the thing I'm multiplying by. It'll only work if this is actually a geometric sequence. I could check it and I could get a value, but then I have to check that value. I have to multiply by that value to see if it continues to give me the next term. Okay? So yes, doing that little division trick will always get me, well, what do I have to multiply by to get from this term to this term? But I have to check it against the rest of the terms is kind of the point there, okay, to make sure this thing is geometric. But that's a trick you can use if you're really struggling and can't identify the thing that you're multiplying by, okay? We've got this nifty little formula here for the nth term of a geometric sequence. If I want to find some term that's way out there instead of having to count out the entire pattern, all right, I can just plug it into this formula. It's a sub n equals a sub 1 times r to the n minus 1, all right? And I really don't like the way I have that written. I should put the parenthesis here and then maybe put that numerator or that exponent in parentheses. Might be a better way to state that, okay? But again, when you plug it into a calculator, it makes more sense to do this guy raised to the n minus 1 in parentheses power, okay? And so, again, the parentheses don't make a huge difference there in terms of this guy, but I want to do a sub 1 times r to the n minus 1. That's kind of the point here, all right? The parentheses aren't super important. A lot of times, I'll write it more like this guy in green because that's more how I'll plug it into the calculator. The calculator might require some of those parentheses, okay? So keep that in mind. Once again, n is the number of the term, a sub 1 is the first term, and r is the common ratio. And when you think about what we did with arithmetic sequences, we started to look at the formula and move some things around. We realized right away that arithmetic was basically a linear equation. It was the format of a linear equation. It was a linear function, just with different variables. Well, this one is the same kind of deal, but it's not linear, it's something else. And as we look at this thing, it should be pretty obvious which one this is. This is an exponential function, okay? It's basically in the same format as, if I kind of draw this over here in a nice little thought bubble, this is basically in the format y equals a times b to the x. And when you think about a times b to the x, a is like the initial amount. It's what we start with. Kind of like a sub 1 is the first term. And then b is the thing you're multiplying by. Well, kind of like r is the common ratio. That's the thing you're multiplying by in this pattern. And so you could really approach every single one of these doing y equals a times b to the x instead of using this formula. It gets a little bit tricky in terms of this n minus 1 thing, all right? But that's just something we kind of have to deal with as we go, all right? And so for this one, let's take a look at an example here. It says find the 11th term. If I want the 11th term of this thing, well, I just kind of have to look at it this way. I have to say, okay, well, I'm going to do a sub 11 because I want the 11th term equals a sub 1. Well, once again, when you label these, this is a sub 1, a sub 2, a sub 3. And so as I kind of work my way through that, I would say, oh, well, a sub 1, the first term here is 2. Okay? And then r, the pattern is that I'm multiplying by 4 each time, so that's a 4. And now raised to the n minus 1, well, that's going to be 11 minus 1, okay? I'm looking for the 11th term. And once again, this is going to be a job for my calculator, okay? This is not one we'd want to do by hand. So I do 4 raised to the 10th power, and then times that 2. So I get a sub 11 equals this guy. So it looks like a 2,097,152, okay? And just like our exponential functions, because this is an exponential function, these things grow really rapidly and really quickly, and they get really big really fast, okay? If you wanted to approach this from the y equals a times b to the x perspective, you would just say, hey, this is the first term, second term, third term. Just think of this in terms of, you just think of it in terms of an xy chart. And so when we write y equals a times b to the x, remember the a value was typically our y-intercept. So once again, work backwards in the pattern. If this continues, this is going to be a 1/2 back here, okay? Because again, working backwards is like dividing by 4, and that's what we did when we graphed these things. So now if I applied that, I said, hey, I'm going to do y equals a times b to the x, a times b to the x. Well, now I'm looking for an x value eventually. If I keep this going, I'm looking for an x value of 11, and I need the y value that goes with it, so I simply plug an 11 into this formula down here. Oh, sorry, I switched colors. Let me go back to green. And if I plug an 11 into this guy, and again, because I changed the a value and put it in that perspective of y-intercept instead of the first term, well, this is going to give me the same thing. I do 4 to the 11th power this time, and then times the 1/2. And once again, I get the 2,097,152. Okay, so you can think of it using that formula, or you can think of it as y equals a times b to the x. Continue the pattern, get that y-intercept, and then plug away. Okay? If I look at the next one, same kind of thing. I start with this guy and say, well, I want the 15th term, so I want a sub 15. That's how we label the 15th term. Equals a sub 1. A sub 1 is the first term, which is 160. Times r to the n minus 1. Well, r this time is 1/2. It's the thing I'm multiplying by each time. And that's why we have to think of it from that perspective. Yeah, it's great that the pattern is divided by 2 each time, but from the perspective of this thing in terms of an equation, I have to write this as the thing I'm multiplying by. I have to write it as a 1/2. And then that's raised to the 15 minus 1 power. Okay, the n minus 1 power, I'm looking for the 15th term, so n this time is the 15. Once again, this is a job for my calculator. I'm going to do 1/2 to the 14th power, which you can just do each of those separately. When you do 1/2 to the 14th power, it's just 1 to the 14th power over 2 to the 14th power, and then times the 160. Actually, let me write this one out. So I've got 160. When I do this to the 14th power, that's 1 over 16,384. And when I multiply that, that's 160 over 16,384. Yes, I'm leaving this as a fraction, because why not? Okay, everybody loves a good fraction. And then, of course, I got to reduce this fraction. And when I reduce this thing, it looks like it reduces all the way down to 512, or sorry, 5 over 512. Okay, that's it. Right? Again, I can do the same thing from the perspective of just y equals a times b to the x. I just have to look at this as an xy chart again. I have to say, hey, this is the first term, the second term, the third term, the fourth term. Well, a in y equals a times b to the x, that's our y-intercept. I got to work backwards. If I keep this pattern going, that's 0 to the 300 and 320 here. If I'm working backwards, it's times 2. So the formula, or the equation, is y equals 320 times 1/2 to the x. And now what I want is I want the 15th term, which is just an x value of 15. It's still the same stuff. It's still the same calculation. It's still going to give me the same result, okay? But it's doing it without memorizing a formula if you're into that kind of thing, okay? And so once again, I get the 5 over the 512. I get the same thing. I'm just talking about different variables. I'm looking at the equation from the perspective of starting at 0 instead of starting at 1, okay? If I look at something like this guy, I want to find the number of that term. The directions aren't really clear here, but I want to find the number of this term. In other words, this is the first term, the second term, the third term, and then all of a sudden I jump out here to what term? What term is this? How many terms does it take for me to get there? And so remember, when we label that, what I'm really asking is, what's the n value? What's the value of n for this term? That's what's telling me the number of the term, okay? And so if I do this from the perspective of plugging this into the formula, I would just say, okay, well, that's a sub n. Here, let me write the formula up here. Equals a sub 1 times r to the n minus 1. And so if I approach it from that perspective, well, when you think about this, when I label this, this is a sub 1, a sub 2, a sub 3. If this is the nth term, well, then it's a sub n. And so if I plug that in for a sub n, when I solve, it will allow me to solve for the n value associated with that term, okay? A sub 1 is a 2, and then this is r is the 4 raised to the n minus 1, and now I'm going to go ahead and solve this thing, okay? The first thing I'm going to do is isolate the exponential part of the function, so I'm going to divide each side by 2. Oh, sorry, wrong color there. And now from here, there are 2 ways for us to solve an exponential function like this. Okay, one of them would be to use logarithms. I would say, hey, you know what? To undo 4 raised to a power, I could do log base 4 of each side. Here, these cancel. I get n minus 1. Well, over there, the log base 4 of 16,384, that's a job for my calculator. And I could plug that into the calculator, doing the natural log of the 16,384 divided by the natural log of 4, and I get a 7. So I get 7 equals, sorry, I switched colors on us again. So we get 7 equals n minus 1. And now I would have to add the 1 over to the other side, and I get n equals 8. Okay. The other option here is, because you know this thing is going to work out nicely, you can always do common bases for these. Okay. When you think about it, the n value has to be a whole number. It has to be a 1, a 2, a 3, a 4, a 5. It has to be something like that. Sorry, not a whole number, a counting number, a natural number. Okay. And so I should be able to get common bases. I just might have to do a little bit of guess and check. Okay. And you probably don't know this, but 16,384 is really just 4 to the 7th power. Okay. And yeah, you'd probably have to do guess and check on your calculator, but now I could set the exponents equal to one another, and I could solve from there, okay? So you just have to make a choice. Do I want to use logarithms, or do I want to get common bases and do a little guess and check, okay? But either way, I find out that this is the 8th term. And once again, I could do the same thing with y equals a times b to the x. The difference is I won't have an n minus 1. I'll just have an x, and I'll solve directly for x when I do the logarithm or when I get the common base and go right to that value of 8. Okay, it'll come out as an x instead of an n. If I look at the next one, same kind of thing. I'm looking at this thing, and hey, this is the first term, the second term, the third term, the fourth term, and then the I don't know term, so I'll call it n, which means this is a sub 1, a sub 2, a sub 3, a sub 4, and a sub n. And so as I plug this thing in, I would say, okay, this is going to be 5 over 16 equals 160 times, well, this was 1/2 for the r value, raised to the n minus 1. Okay, and once again, I'm going to divide each side, so I'm going to divide each side by the 160. Again, dividing by a fraction, same as multiplying by the reciprocal. If you need to take that kind of off to the side, that would be fine. It's basically like 5 over 16 times 1 over 160, if you want to think of it that way. And it looks like that's going to reduce to a 1 over 512. And then again, from here, you could get common bases. Maybe I'll do that this time since I kind of showed the logarithms. You could take log base 1/2 of each side and go from there. Or you get common bases. You say, hey, you know what? 512 or 2 to what power gives me a 512? And it's actually 2 to the 8th power, I believe. So this is going to be 2 to the negative 8th. Oh, sorry. No, it's not 2 to the 8th. It's 2 to the 9th power. I guessed wrong. I'm ashamed of myself. So this is going to be 2 to the negative 9th power equals 2 to the negative 1st power in terms of the n minus 1. And now I have the common base. I can set those exponents equal to one another. In other words, I get negative 9 equals the negative n plus 1. I can subtract that 1 from each side, and then divide by the negative. So that's the 10th term, okay? And so once again, as I look at that, my preference is just to simply use logarithms. It takes me longer to guess and check in terms of getting that exponent than it does just take the log base 1/2 of each side, okay? Last thing here, let's talk about geometric means. The geometric mean, once again, means when we have non-consecutive values. So I'm missing terms in between here. So terms between any non-consecutive terms in a geometric sequence. And once again, to get from one term to the next in a geometric sequence, I simply just needed to know, what do I multiply by to get from one term to the next, okay? That's the thing I'm looking for. And so to do that, once again, I just plug it into my formula. I say, you know what? I've got a sub 1 here. This is the first term. I'm missing the second term, the third term, the fourth term, and the fifth term. the fifth term I have. And so I just have to kind of work with what I have. I say, you know what? I know the first term is 16. I know the R value is the thing I'm looking for, so that's my variable. So I need an N value and a term that I can plug in together. Well, that's where that 256 comes in. 256 is a term, and it's associated with an N value of 5. And so from here, I just plug away. So here I divide each side by the 16, which gives me a 16. Sorry, I guess I should write it. 16 equals R to the fourth power. And now I take the fourth root of each side. Okay? And so what I get is R equals 2. And so that's not what the question asked for. It asked me to fill in these blanks, so times 2. So times 2 is a 32. Times 2 is a 64. Times 2 is a 128. Times 2 is a 256. It automatically checks itself. Okay? So there's the geometric means. There's those missing terms. Okay? And what will happen a lot of times is students will just start guessing and checking for these. But look at something like this one. To get from 16 to the 160,000, guess and check isn't always the best option, especially if I give you one that's really weird and has like a square root or something in it. That would be really mean of me. Hint, hint, wink, wink. All right, so when I do this, make sure you understand how to do this in the formula. Don't just do guess and check. And so once again, I've got the first term. I'm missing the second. I'm missing the third. But I do have the fourth, okay? And so I plug this in. I say, okay, well, if I use this guy as the term, the first term is this, I can use now an N value of 4, okay? So I basically use this guy like an ordered pair that gets plugged in, the N value of 4 and a term of 160,000. And so once again, I divide each side. So I'm going to divide each side by 16. So over here, let's see, I get a 1 with a couple zeros behind it, equals R to the third power. And now I take the cube root of each side. And when you take the cube root of each side here, you could plug this into your calculator and say, okay, I've got the 10,000, the cube root of 10,000. And it gives me a 21.54 something. But the problem is if I do that, well, it's not going to work out very well. I'm not going to get to this 160 exactly because I'm rounding off. So I'm literally just going to leave it as the cube root of 10,000. You could simplify that a little bit. But again, I'm not asking you for the R value. What I'm asking you for are the missing terms. And so that's what I have to multiply by. So on my calculator, I'm going to take the 16 times the cube root of 10,000. And now I'll round that off a little bit. It gives me a 344.7. And now I'm going to take that without rounding it off on my calculator and multiply it by the cube root of the 10,000. And it gives me a 7426.5. And then once again, without rounding it off, I'm going to multiply that value that my calculator just spit out for me. And I'm going to multiply it by the cube root of 10,000. And it should give me exactly 160,000, and it does. Okay? So again, don't do guess and check. Make sure you understand how to find it officially, especially if it comes out to be a strange number that has a square root, or in this case, a cube root. Okay?